Okay, so we want to switch our focus to talking about some special subspaces or special subsets of three-dimensional space, and that's lines and planes. And so I'm sure you know a good bit about lines in the plane. It's just y equals mx plus b kind of stuff. But lines in space are a little bit more complicated. So a line in space, so I'm thinking like R3, is given by a point on the line. Let's just say that's point is ABC, and a vector pointing in the direction of the line. Let's say that vector is V. Then the equation of a line is the position vector of the point, so A, B, C, plus the vector in the direction of the line times this parameter t. So this is also called the vector equation of the line. And so this t is what's called a parameter. So it's parameterized by t. We're going to talk a lot more about parametric equations and vector valued functions, but this is just sort of an introductory example. So we have this line, and the idea is that for each value of t, I'm getting a vector pointing to a point on the line. So let me draw a picture. So let's say here's the origin, 0, 0, 0. Well, I just told you that to have this line, we have a point on the line, A, B, C, and then a vector pointing in the direction of the line. So my actual line is going to be passing through space like this. But you see the vector will just be pointing in the direction of the line. Okay, so this vector here is the vector A, B, C, which is the position vector of this point. And so any point on the line I can think about as, well, it's just V, but I've rescaled V, so say this is t times V, right? So there's going to be some value of t, so I can just rescale V to this point. But then the vector that points to this point on the line, that I'm calling this L of t, really is just this position vector plus the scaling of the direction vector. So that's the vector equation of the line. And it also leads to what's called the parametric equations of the line. So I can just sort of write the x component as, well, a plus the x component of the direction times t. And then y, so I'm just actually writing out what the components are as a function of t. This is going to be b plus byt, and then the z component will be c plus bzt. And this is called the parametric equation of the line. And it's really the same thing as the vector equation. It's just sort of broken up into 3 different coordinate functions. So in a plane, we know there are really just a couple of cases for lines. So in the plane, so like in the xy plane, so lines can coincide, meaning they're the same line. Lines can be parallel and not coincide, meaning they have the same slope but different y-intercepts. And then lines can, so if they don't coincide and they're not parallel, lines can intersect in exactly 1 point. So those are sort of our conditions for a line. In space, it's a lot more interesting. It's actually a lot rarer for lines to intersect. And just think about if you have 2 planes in the sky. Well, it's going to be a lot harder for the planes to run into each other because not only do they need to be kind of flying in the same plane, they also need to line up at exactly the same time. So in space, of course, lines can coincide, lines can be parallel. So what does it mean for 2 lines to be parallel in space? Well, their direction vectors are parallel. They can also intersect in a point. But there's also a fourth thing that can happen. And actually, this is probably the most common thing to happen. They can be what's called skew. And so what I really mean by skew is they lie in different planes. But if you look at the picture, so if you have a line here, then I could have another line that goes kind of across it, but instead of going and intersecting it, it goes underneath it, like that. So these are skew lines. So in space, they're just sort of kind of arbitrarily going in different directions, and they don't happen to hit. Sort of like 2 planes flying, right? They can just be kind of skewed like that. So the other interesting object we can talk about in space is a plane. And vectors are really going to allow us to describe planes really well. So a plane in space is given by a point in the plane and what's called a normal vector. And what is that? It's a vector that's orthogonal to every vector in the plane. And so the vector equation of a plane is just, okay, so if n is this normal vector, so normal vector n, then, and let's say our point is again a, b, c. So we have a point a, b, c and a normal vector n, then the equation of the plane is just going to be, well, I'm going to take my vector, normal vector n, and dot with any point, with any vector in the plane, or any vector kind of rooted at this point that's in the plane. So y minus b, z minus c. So this vector x minus a, y minus b, z minus c is just sort of any vector that is rooted at this point a, b, c. And now I want these vectors to be orthogonal to this normal vector. So I want their dot product to be 0. So we can expand this and write, okay, the x component, so just write out what the dot product is. We'll get just a simple linear equation of the plane. And now nx, ny, and nz are known numbers. Those are just the components of the normal vector. A, b, and c are known numbers. Those are just the coordinates of the point in the plane. X, y, and z here are the variables. So if you want like an example, you can have x plus y plus c equals 1 or something like that. And so let me try to draw a picture of what's going on here. So if we have a plane, look at this. Of course, it extends out infinitely in every direction. Then I can have my point A, B, C, and then I have some other point, X, Y, Z, and I'm letting this be any point for now, but if I have this normal vector, so it's going to be perpendicular to the plane, so I sort of root the plane in the point, and then, so if you take like a piece of paper and put it on the end of a pencil, it's fixed to that pencil, but then it can still sort of rotate around that point. But as soon as I have a perpendicular direction, it's fixed. I fix the plane. And so I want to take these vectors rooted from A, B, C. So this is this vector x minus a, y minus b, z minus c, right here. And I want all of these such vectors that when I take the dot product with n, I get 0. And then I expand out, and this is exactly what I get. So this is the equation of the plane. Okay, so just a couple quick facts about planes. So if I have two vectors, u and v, in the same plane, and this is normally how I figure out what a plane is. I have two vectors, and two vectors will lie in the same plane. then what I can do for the normal vector of the plane, recall that the cross product of u and v will be orthogonal to both u and v. So if I want a normal vector for my plane to write down the equation, it's typical to use the cross product of two vectors that are in the plane. So this is orthogonal to the plane. And when I say orthogonal to the plane, I mean orthogonal to every vector in the plane. Okay, so then I just need a point. I can write down the equation of my plane. So also, two planes are parallel if their normal vectors are parallel. And so you can just sort of play around with two pieces of paper and you can sort of see what I mean. So if they're parallel, they're sort of laying flat parallel to each other, and so their normal vectors are going to be parallel in that case. And so two planes that are not parallel, or of course they don't coincide, will intersect. And what will their intersection be? So two planes that are not parallel intersect in a line. So the intersection of two planes is either empty if they're parallel, or it's equal to a line. So these are just kind of some useful facts about planes when we're working with them. Okay, so the last thing we want to talk about is sort of distance in space, distance between objects in space. So we know the distance between 2 points is just going to be the length of the vector lying between them. So A minus E, B minus F, C minus G. That's just the distance formula. It's sort of what we use to define the length of the vector. But what about the distance between point and a plane? So what do I even mean by that? So let's say I have this plane, and I have a normal vector here, and I have some other point here, A, B, C, and so what do I mean by the distance between this point and this plane? Well, if I take a point in the plane, say x, y, z, and I draw this vector. Okay, so this is going to be a distance, may not be the shortest distance. And what I can do is I can actually project this vector onto the normal direction. So if this is this vector b, then I can project b onto the normal direction. And that will give me the vector of the shortest length, because it'll sort of be this vector that'll be perpendicular to the plane. So it's like a straight line between the line and the plane. So I want to use the projection vector. There's also the question about the distance between two lines. So specifically two skew lines, right? Because if they intersect, of course the distance will be 0. So if I take a line with a direction vector v, I take a line with a direction vector u, well, it's the same sort of idea. I want to just take any vector, say w, connecting 2 points on the line, and I want to project it onto a vector that's normal to both of v and u. So the distance is actually just going to be given by, or I should say the vector that gives me this, that has the shortest length connecting the two lines is going to be the projection onto, well, some vector that's normal to both v and u. Well, we're just going to use the cross product again. So the projection onto the cross product of, just take your favorite vector connecting the points between them. So this is, we're not going to talk a lot about this because it's not going to play a huge role later in the course, but it's just sort of this neat geometry thing where you can use this projection vector to find distances between objects in space. Okay, so we want to find the vector equation of the line passing through the points 1, 0, 0, and 1, 1, 1. So we have actually 2 points on the line. We only need 1 point on the line. But the other thing that we need is a vector pointing in the direction of the line. But the vector pointing in the direction of the line, we can just use the vector pointing between these 2 points. So for our direction vector, we can just use 1 minus 1, 1 minus 0, 1 minus 0. Right here. So just this vector pointing between this point and this point, which is just 0, 1, 1. So then our equation of our line will just be, we'll take your favorite point here. I'll just take 1, 0, 0, and then add our direction vector, which is 0, 1, 1, times t. So here's the vector equation of the line, and we can write this as just 1 t, t, like that. And you see, if we take t is equal to 0, we get this point, and if we take t equal to 1, we get this point. So this line really does pass through both of those points. Okay, so we want to determine the equation of the plane containing these points. And now, for a plane, we need a point in the plane. We have plenty of points in the plane. And then the key thing is this normal vector. So it's a vector that's orthogonal to every vector in the plane. And we sort of found a hint, and that was to use, okay, if we have 2 vectors in the plane, we can use the cross product. So that's going to be a good place to start. So notice that we have a vector u, which is, well, we have a few options. So we can definitely take 1, 0, 0. So that's the vector connecting this point and this point. And then we have another vector, let's see, 0, 0, 1. So that's the vector connecting this point and this point, lie in the plane. So we can take the normal vector, u cross v, will be orthogonal to the plane. And so what is u cross v? Well, u cross v, well, there's only going to be one component that's not 0. And that's going to be exactly the k component. And the y component. So let's just write it down. So we have it. So this is 1, 0, 0, 0, 0, 1. And so this is going to be 0. This will be -1. This will be 0. Okay, so we have our normal vector. It's good. And so now our plane will just be 0, -1, 0. And now we need to dot with any point based at a point in the plane. So we can use, say, 1, 2, 3. So like 1 minus x, 2 minus y, 3 minus z. Okay, and what do we get? We want this to be 0. And so if we actually do this product here, we get 0 plus -2 minus y plus 0 is equal to 0. But then this is just the plane y is equal to 2. Okay, so we want to find the distance between this point and this plane. And the key hint here is that we want to project onto the normal vector. So we want to take a vector connecting the point and any point on the plane and then project it back down onto the normal vector. So what is the normal vector? Well, notice that we can write x plus y plus z equals 1 as 1, 1, 1 dot x minus 1/3, y minus 1/3, z minus 1/3 equals 0. So what that tells us is that 1, 1, 1 is normal to the plane. So this is the vector we want to project onto. So then we need to take a vector that connects the point in the plane. Well, let's just take, okay, x, we'll take a point and then subtract 1, and then we'll take y and subtract 0, and we'll take z and subtract 1. So this is going to be any vector starting from the point 1, 0, 1. But we have this relationship, x plus y plus z is equal to 1. And so what we can do is we can solve for y. So y is equal to 1 minus x minus z. And so actually, I can take this vector u to be x minus 1, 1 minus x minus z, and then z minus 1. And this will be a vector from 1, 0, 1 to the plane. Then the vector that's going to minimize the distance is going to be the projection of this vector u onto the normal vector v, which recall is u dot n divided by the length of n squared, and then in the direction of the normal vector. Okay, so what is u dot n? Well, u dot n is just going to be, I'm just going to add up x minus 1 plus 1 minus x minus z plus c minus 1. So x minus 1 plus 1 minus x minus c plus z minus 1 all over the length of the normal vector squared, which is just 1 squared plus 1 squared plus 1 squared, so 3. And then 1, 1, 1. Now notice what happens up here. We have x minus x and minus z plus c. So those go away, and we're left with negative 1 plus 1, which is 0, and then negative 1. So negative 1/3, 1, 1, 1. And so the distance will just be the length of this vector, which is going to be what? Well, it's going to be, so each component is going to be 1/3, so the square root of 1/9, 1/3 squared, really negative 1/3 squared, 1/9, 9th, and what is this going to be? It's going to be square root of 3 divided by 3. It's going to be the distance between that point and that point. All right, so to find the distance between these two lines, I'm going to write them, they're kind of in parametric form. I'm going to write them in vector form. So I'm going to write this as 1, 2, 3 plus 1, 1, 2 times t. And I'm going to think about this as this direction vector u. And I'll write this guy as 0, 0, 1 plus 1, 2, 1, t. And I'll think about the direction vector as v. Okay, and so we saw a hint about how to find the distance between these two lines, and they are in fact skew. To project a vector connecting the two lines onto a vector normal to the two lines. And so the two directions are u cross v, so what we can do is we can find a normal vector to both by just taking u cross v. Okay, so what is u cross v? Well, we should be masters of the cross product now. So we have 1, 1, 2, 2, 1. So our vector will be, let's see, looks like negative 3, and then let's see, minus 1, minus 2, so just 1, and then 2 minus 1, 1. Okay, so there's our normal vector. That's good. And now we just want to take any vector connecting the 2 points. All right, so, well, here's a point on the line. If I just take t equals 0 in both cases, I know the point 1, 2, 3 is on this line, and 0, 0, 1 is on this line. So that tells me that u equals 1, 2, 2 connects points on the 2 lines. And so the trick, I mean, really with any of these distance problems, is always projecting back to the normal direction. That's always going to give the shortest direction. So then the vector that's going to give us the shortest distance is going to be the projection onto this normal vector, this vector u, which is going to be, let me just write it down, n dot u divided by length of n squared, and then in the direction of n. So the dot product of n and u is going to be -3 plus 2 plus 2, so 1. And then the length of n is squared is 3 squared plus 1 squared plus 1 squared, so 11. And then n is -3, 1, 1. Okay, but the distance is going to be the length of this vector. So that's literally the vector that is that gives the shortest distance. And so the distance is just going to be the length of this vector. Which is, okay, so the components are 3 over 11, 1 over 11, and 1 over 11. So square root of 3 over 11 squared plus 1 over 11 squared plus 1 over 11 squared. And what is that going to give us? It's going to give us square root of 11 divided by 11 is the distance between those two lines.